GCE Advanced Level Chemistry Practical Series, experiment number 29. Tests for aniline. So we are going to be looking at different types of tests that we can do to identify the presence of aniline. The aim of this practical is to identify aromatic primary amines by chemical reactions of diazonium salts and to form azo-dyes via diazonium salts. So we will be forming diazonium salts starting from aniline, and then we are going to be reacting this diazonium salt with other aromatic compounds like phenols and beta-naphthol and convert these diazonium ions or diazonium salts into azo-dyes. And let's take a look at the introduction. Commercially available organic dyes are used in many industries such as food and clothing and paint. Azo-dyes are one such commonly used class of synthetic dyes. All azo-dyes have the basic structure AR, N double bonded to another N and AR. So what they're trying to communicate here is azo-dyes is a synthetically produced type of dye which is widely used in many industries such as food, clothing, especially clothing, and paint. And when it comes to the structure of azo-dyes, we can see there are two nitrogens connected to one another with a double bond, and on either side of each nitrogen we have a aromatic compound or something that is connected to benzene is going to be there attached directly to nitrogen. And they say AR and AR dash are aromatic groups in this structure. What they represent by AR and AR dash are aromatic groups. In the laboratory experiment, aniline is converted to a diazonium salt which is then reacted with beta-naphthol or naphthalene 2-ol to produce an azo-dye. In this case, we are using phenol or beta-naphthol, not just beta-naphthol. Beta-naphthol has another name. The actual name is naphthalene 2-ol, or else we can actually call it 2-naphthol as well. So this is the introduction to our practical. In summary, in our practical, what we are trying to do is take aniline and then react it with the correct reagents to form benzene diazonium chloride, and then this benzene diazonium salt, which is benzene diazonium chloride, is going to be reacted with phenol to form an azo-dye. Let's move on to the next slide. Now students, we are going to be looking at how to convert aniline into benzene diazonium chloride. So we have aniline here, which is a primary aromatic amine. Whenever the nitrogen is directly connected to the benzene ring, we form a aromatic amine. This is a primary aromatic amine. Now students, if you take a look at how this conversion is done, we have used sodium nitrite and dilute HCl. So when these two things are added together, we form nitrous acid, HNO2. HNO2 will be formed when these two things are reacted together. So this nitrous acid, when it is reacting with aniline, you will be forming this compound, which is a salt benzene diazonium chloride. So this particular salt that is formed here is not very stable at higher temperatures. So if you are conducting this experiment at higher temperatures, we would not obtain this benzene diazonium chloride. So whenever we are trying to convert aniline into benzene diazonium chloride, we have to use very small temperatures, like lower temperatures such as 0 to 5 degrees Celsius. If you are employing higher temperatures like room temperature, you will not be forming this. Instead, you will be attaching here a phenol or OH group and overall product that is formed is a phenol. Now, let's move on to the next slide. In this slide, we are going to be learning what the actual structure of benzene diazonium chloride is. Now, in the previous slide we referred to the benzene diazonium chloride in this manner. If you have N2 plus NCl minus. So what do we mean by this? What is the actual structure? So actual structure is here. The actual structure is given here. So let's focus on that mainly. You can see the nitrogen. One of the nitrogen is directly connected to the benzene ring, and that nitrogen is forming a triple bond with another nitrogen atom. So this nitrogen has 4 covalent bonds and no lone pairs. So because of that, that nitrogen has a positive charge on it. When it comes to the second nitrogen atom, you can see it's only having 3 bonds and a lone pair is definitely going to be there on it. But most of the time you will see the Cl is written next to this nitrogen. That is mainly for convenience when you're trying to write the structure. However, in actuality or in reality, what happens is you can see the chloride ion is attracted to the positively charged nitrogen that we have here, right? So when we are actually considering where the chlorine is now present as a chloride ion here. This chloride ion is actually attracted to the positively charged nitrogen. Although we summarize it and write it like this, you have to always keep in mind nitrogen over here is not the one that is attracted to the chloride ion. The chloride ion and the positively charged nitrogen are the ones that are attracted to one another. So now we know when you are writing this compound where we write N2Cl, we need to remember when you write N2Cl like this, you need to remember where the positive charge is. Positive charge is in the nitrogen that is directly connected to the benzene ring. Now, let's move on to our next slide. Reactions of benzene diazonium chloride. What type of reactions are actually taking place when it comes to benzene diazonium chloride? Benzene diazonium chloride will react with phenol in alkaline medium. Phenol in alkaline medium to produce an orange color azo dye compound. So you can see the reaction that is given here. As you react our benzene diazonium chloride or benzene diazonium salt with phenol, phenol is a ring activator, or not the phenol, basically this OH group that is present on phenol is a ring activator. It activates mainly the ortho and the para positions of the benzene ring. And as they react in alkaline medium, the para hydrogen actually gets removed along with the Cl- ion in the benzene diazonium chloride and will be forming this compound, p-hydroxyazobenzene. You can see that this is an azo dye. Why? When we were talking about azo dyes, one of the things that you learned, was that they have this structure. You have 2 nitrogens, and on either side of the nitrogen, you have to have a aromatic compound connected. And we can see that situation here. We have a OH group on the right hand side corner, but the basic structure of an azo dye is seen when it comes to p-hydroxyazobenzene. To not take away the attention from the main structure, I will erase this here. And now students, you can see that the p-hydroxyazobenzene, or this structure that is formed, is going to be orange in color. It is very important for you to remember the color of the compound that is formed when phenol is reacted with benzene diazonium chloride. It is very important for you to remember the color. The name might not be discussed in the syllabus, so it is mainly the color that is going to be very important for you to remember. And at this point, students, you have to understand what has happened here. You can see the hydrogen here is replaced by another group, and what has acted as now you can see when it comes to benzene ring related reactions, we always come across electrophilic substitution reactions. Now benzene ring has a high electron density due to delocalized electron cloud in the benzene ring. So normally they are more prone to electrophilic substitution reactions. So what you see here is also an electrophilic substitution reaction. Now tell me, what is acting as an electrophile here? You can see this ion, benzene diazonium ion, is acting as an electrophile. This is the ion that is acting as an electrophile. And the reaction that is taking place here is going to be a electrophilic substitution reaction. Now let's move on to our next slide. So in this slide that we have over here, we are taking a look at another reaction. How benzene diazonium chloride salt will react with beta naphthol in alkaline medium. Again, we are employing an alkaline medium. We'll be learning about, actually we can talk about why we use an alkaline medium. Now beta naphthol, or even when it comes to phenol, they are not very soluble in water, right? But the salt that is that we have over here is a water soluble salt, and when you're trying to react these two together, it is important that we somehow bring these phenol and beta naphthol into a water soluble form, or we have to make aqueous solutions out of these two. And how do we do that? By reacting these phenols with an alkaline medium. As you know, phenols can donate this hydrogen in alkaline medium and form phenoxide anion. So we will be forming sodium phenoxide, which is soluble in water. So at that point, we can carry out this reaction without any issue. That is why we are employing a alkaline medium. Now we can see here when it comes to beta naphthol or 2-naphthol. One of the reasons why we call 2-naphthol is when we are numbering this carbon chain. This is carbon number 1, this is carbon number 2. This is how we normally number beta naphthol, and on the second carbon we can see there is a OH group that is there. So that's why we call it 2-naphthol or beta naphthol. And when it comes to this benzene ring, you can see now in the previous reaction it was the para-hydrogen that was removed when we are trying to react it with benzene diazonium chloride. But when it comes to benzene diazonium chloride reacting with beta naphthol, is it the para-hydrogen that is getting removed? Actually, you will see here para-hydrogen is blocked, right? The para-hydrogen that we have over here is blocked. So therefore, you will be resorting to removing one of the ortho hydrogens. So that is why the product that is formed is going to be formed like this. You can see the ortho hydrogen reacts with the Cl minus here, or gets removed with the Cl minus here, and the nucleophilic group is going to be attached to the first carbon that we have over here, or carbon that is labeled as number 1. So the product that is formed, the structure of the product is given here. Again, we have the same structure. We have 2 nitrogens connected via a double bond, and on either side of those 2 hydrogens we can see an aromatic group connected to the nitrogen. And the compound that is formed is going to be a red color azodide, or red color compound will be formed. So students, this is a very important piece of information that you should have with you. And when it comes to reactions such as this, what you do to identify whether we have completed the reaction properly is the formation or observing the formation of a red color azodide when it comes to benzene disonium chloride reacting with beta-naphthol, or when it comes to phenol reacting with benzene disonium chloride. How we identify that the reaction has gone to completion is by observing the formation of a orange color azodide. Here also, this is going to be an electrophilic substitution reaction, and the electrophile is this. Now, one of the important facts about benzene disonium salts are given here. Very important. Benzene disonium salts react with aromatic compounds that contain a strong activating group groups such as OH or NH2 and form azo compounds. So these electrophiles. Now, first of all, if you are somewhat not understanding what an electrophile is a group that loves negative charge. So electro refers to electrons or negative charge. Phile refers to loving. So an electrophile is a negative charge loving group. And why do they like negative charge? Because they are currently electron deficient, or there is an electron deficiency in them. You can see this electrophile is having a positive charge, so therefore it is more prone to attack groups that are rich in electrons. So benzene might not be that rich in electrons compared to a benzene or aromatic compound with OH groups or NH2 groups. These OH groups and NH2 groups make their lone pairs get incorporated into the delocalized electron cloud of benzene, and then activates the benzene ring or increases the electron density that you normally see in the benzene ring, making it easier for these kind of electrophilic groups to attack the benzene ring. In this reaction, the disonium ion acts as an electrophile, as you have seen before as well. Now everyone, we are going to be observing how the reaction we spoke of on the previous slide is taking place here. You can see that this reaction is taking place between benzene disonium salt and a compound that contains a group which happens to be an activating group or ring activating group. Now, ring activating groups normally have a lone pair of electrons on them, which is going to get incorporated into the benzene's delocalized electron cloud, and therefore activating the benzene ring, or therefore increasing the electron density inside the benzene ring. So as this reaction happens, as usual, we can see hydrogen, or in the para position, gets removed with the chloride ion, forming HCl. Right, you will be seeing the formation of HCl at that point, and the compound forms, or these two react to form an azodide compound. Now, azodyes will range in color mostly from yellow to a red color. So depending on the group that is attached here, or depending on the type of aromatic compound we are reacting it with, you will end up getting a differently colored azodide. So these kind of electron releasing groups such as OH, NH2, NHR, R is representing a alkyl group, or NR2, nitrogen that is connected to alkyl groups. All of these are capable of releasing their electrons into the delocalized electron cloud of benzene, and thereby activating the benzene ring. So they end up forming azodide compounds. And when it comes to all of these reactions that take place, there are also going to be electrophilic substitution reactions, and the electrophile, as usual, is going to be our benzene disonium ion. Now let's move on to our next slide. Now students, we are going to be looking at how decomposition of benzene diazonium salts take place. Aromatic amines. Now this is a very important note, so please pay close attention. Aromatic amines such as phenylamine, or what we have referred to as aniline so far, will react with nitrous acid HNO2 and HCl to produce an aromatic diazonium salt. We know that already. We have studied that. We took aniline and then we reacted it with sodium nitrite and HCl at a very low temperature such as 0 to 5 degrees Celsius, and we formed this compound which is aromatic diazonium, or which is a aromatic diazonium salt, or benzene diazonium chloride, which will undergo decomposition at room temperature to produce phenols. So students, one thing that you need to understand is this particular benzene diazonium chloride or aromatic diazonium salt is not very stable. So that is why we are employing such low temperatures, 0 to 5 degrees Celsius. We employ 0 to 5 degrees Celsius, very small temperatures, to make sure that this decomposition won't take place. Instead, we will obtain the benzene diazonium chloride. Otherwise, if you are going to conduct the same experiment in just normal room temperature, what happens is this benzene diazonium chloride salt will undergo decomposition to form phenol. So this group that you see over here will be turned into an OH group. This will happen at room temperature. If you are conducting this experiment at room temperature, the final product that you're going to obtain is phenol. So to avoid that from happening, we are going to be doing this experiment at very low temperatures. However, you need to know what takes place at room temperature. At room temperature, the benzene diazonium salt will turn into a phenol group, releasing nitrogen gas and HCl. Releasing nitrogen gas and HCl. Aromatic diazonium salts are more stable compared to aliphatic diazonium salts. That is a very important observation. Aromatic diazonium salts are more stable compared to aliphatic diazonium salts. Now, in most of the questions that normally you come across when it comes to your final exams, you would note that they are trying to see if you understand this part of information or this specific information. They want to see if you understand that aliphatic compounds, when they are forming diazonium salts, they are not going to be stable, right? You can't decrease the temperature and form an aliphatic diazonium salt. You can only form a aromatic diazonium salt at low temperatures. You can't do the same with aliphatic diazonium salts. So that is a very important piece of information. At lower temperatures, the decomposition of aromatic diazonium salts into a phenol can be prevented. Actually, it can be slowed down to the point where you don't form the phenol, right? So at lower temperatures, due to comparatively high stable nature of aromatic diazonium salts, when you are decreasing the temperature enough, conversion of the diazonium salt into a phenol can be slowed down sufficiently to produce benzene diazonium salt. So we can say at low temperatures, formation of phenol can be prevented. Then the diazonium salt can be obtained separately. Because of this, at low temperatures, in the presence of an acid such as HCl or sulfuric acid, aniline can be reacted with nitrous acid to form benzene diazonium salt. So what this means is, students, this reaction can only successfully be done at lower temperatures such as this. As we do the same experiment at higher temperatures, instead of forming the benzene disonium salt, you'll be forming phenol. And what about aliphatic? What about aliphatic amines? So what if you have an amine such as this one? There's also an aliphatic primary amine. What will happen here? If you employ the same conditions, if you use the same conditions, right? We use sodium nitrate, dilute HCl along with the temperature 0 to 5 degrees Celsius. Will you be forming aliphatic disonium salt? Will you be forming an aliphatic disonium salt? The answer is no. Instead, you will be forming an alcohol. Instead, you will be forming alcohol along with nitrogen gas and HCl. Right, so keep in mind, students, when it comes to the same conditions, if you're trying to convert a primary aliphatic amine into a disonium salt, that will not happen. Primary aliphatic amines don't form disonium salts. Now, aromatic amines do form disonium salts. For it to be an aromatic amine, keep in mind the nitrogen in the amine should directly be connected to the benzene ring. If it is not directly connected to the benzene ring, it is not going to be considered an aromatic amine. Right? So if you have a compound like this, if you have a compound where you have the nitrogen not directly connected to benzene, such as this situation, this will not be considered a aromatic amine. This is an aliphatic amine. So therefore, this will also not form a disonium salt. This will be forming an alcohol. As you react it with sodium nitrite with HCl and employ a temperature of 0 to 5 degrees Celsius, you will not be getting a disonium salt. Instead, you will be getting an alcohol. So we have to keep that in mind, students. And then let's move on to the next slide. In the next slide, we are going to be looking at reactions in which disonium group is replaced by another atom or a group. So reactions of disonium salts with water. That's the first reaction that we come across. Reactions of disonium salts with water. So let's take a look at what happens here. So after forming the benzene disonium salt, if you react it with water and actually heat the mixture up, what happens is, again, phenol will be formed. So what do we know? This disonium salt will not be very stable at higher temperatures. We know a few things. We learned that aliphatic disonium salts are not stable at all to be formed. When it comes to aromatic disonium salts are more stable compared to aliphatic disonium salts. So therefore, at lower temperatures, we can prevent its decomposition and form the disonium salt. But if you increase the temperature, what happens is the disonium salt will get decomposed to form a phenol and nitrogen gas and HCl. Phenol, nitrogen gas and HCl will be formed. So this is the reaction that you would normally see with water. How about with some other compounds? Now let's take a look at them. When aliphatic amines are reacted to form disonium salts, the produced disonium salt will immediately undergo hydrolysis to form an alcohol, as we saw earlier. But we are now seeing it with examples. aliphatic amines. Aliphatic amines are quite unstable. Not aliphatic amines, sorry. We are talking about aliphatic diazonium salts that are made through the aliphatic amine. Anyhow, aliphatic diazonium salts that are made are quite unstable, so they will immediately undergo hydrolysis to form an alcohol. So you can see some examples here. Now this is due to the fact that diazonium salts, especially aliphatic diazonium salts, are quite unstable. Few examples are given below. So if you take this aliphatic amine, when you are reacting it with dilute HCl and sodium nitrite, you will be forming nitrous acid. And they have not mentioned a temperature here, or we have not mentioned a temperature here, because at any temperature it is not going to be stable. So therefore you will not be forming a stable diazonium salt. Instead you will be directly forming our alcohol. Right, so you can see here, although we have written here the aliphatic diazonium salt is formed, this formed aliphatic diazonium salt immediately undergoes hydrolysis because it is not stable and form an alcohol. This is one of the questions that you will see when we are discussing questions also. You will see that this type of question is going to be tested in your final exam. Again, another amine, you can see CH3, NH2, methylamine. When you are reacting methylamine with the same reagents, sodium nitrite and dilute hydrochloric acid, you are going to come across the same observation, same product. You don't see the aliphatic diazonium salt. Instead, you are going to be seeing the alcohol being formed. That is true for all of these amines that is listed here. Right? You can see when this reaction is summarized here, when we are using ethylamine, you will be seeing the same reaction where you will be forming only an alcohol. When you are talking about this final compound also, you can see we will form the same compound, an alcohol, instead of forming a aliphatic diazonium salt. Now students, let's move on to the next slide with that information. At this point, we are going to be starting our practical. So to conduct our practical, we are going to be looking at what are the reagents we will be needing for our practical. So for our practical, we'll be needing some equipment as well as some chemicals. The equipment are quite simple. We have test tubes and ice bath. You might have come across a water bath. What is an ice bath? Basically, ice bath is a beaker filled with ice. And we will be placing our test tubes containing our reagents in the ice bath. Due to the low temperature of ice, it will bring the temperature of our solutions also down between 0 to 5 degrees Celsius. And chemicals, we'll be using sodium hydroxide and we'll be using aniline. The structure of aniline is given here. We commonly refer to this as aniline. Sometimes some of you might know it to be or know it from a different name, phenylamine, right? So phenylamine, aniline, both are the same thing. We have phenol here and we have 2-naphthol or beta-naphthol that is given here. And we'll be using sodium nitrite and HCl. So sodium nitrite and HCl together, you should remember, we'll be forming nitrous acid. So these are the reagents that we'll be mainly needing for this practical. One of the precautions you should be taking, or one of the things that you should be informed about when we are handling these reagents, is that aniline is a toxic substance and you should be avoiding skin contact when you are carrying out this practical. So you should be wearing your personal protective equipment such as gloves when you are carrying out this experiment. Now let's move on to the next slide. In this slide, we are going to be looking at what experiments we are doing to identify the characters of aniline. So you can see we have taken a small volume of water. We will be taking a small volume of water and we'll be adding that to aniline. We can see a layer separation when you're adding aniline and water together. Aniline is a organic substance and water is a polar solvent. Now these two things do not mix well together. These two things do not mix well together. So therefore you will be observing a layer separation. You will be observing a layer separation. So aniline has a slight yellowish color. If it is quite impure, then it will be getting darker in color, but in its most pure form it is going to be somewhat clear and having a little bit of a yellowish color. And when you are reacting aniline with water, you will be seeing a layer separation. However, if you add HCl to aniline, we can see the aniline is starting to dissolve in water. That is due to they are forming an ion, phenylammonium ion, which will be water soluble. So if you take aniline, I will represent aniline this way. If you take aniline and react it with HCl, it will form phenylammonium chloride. This is going to be positively charged and chloride ions will be there in the medium. So you'll be forming the compound phenylammonium chloride. Phenylammonium ions are soluble in water. So the solubility of aniline will improve upon addition of concentrated hydrochloric acid. So if you want to dissolve these two immiscible layers together, you can add concentrated hydrochloric acid, where aniline will react to form phenylammonium chloride, which is going to be soluble in water. Now, let's move on to our next slide. Now, in this second slide, we are going to be looking at another reaction. Reacting aniline with bromine water. Reacting aniline with bromine water. Now, students, when it comes to aniline, like I mentioned earlier, is a strong ring activator. These lone pairs that are present on nitrogen can get delocalized into the benzene ring. So therefore, you will form a few resonance structures which will give you a very clear idea why we consider aniline to be a strong ring activator. We will be looking at those resonance structure during the time that we discuss some questions for this practical. However, I want you to be aware about the fact that aniline, or the NH2 group in aniline, is going to activate the benzene ring really well, so that when benzene ring comes into contact with bromine, they immediately react to form a white color precipitate, and the color of bromine will disappear. Bromine water is going to be brown in color, and as they react, the formed solution is going to be colorless. You wouldn't have a brown coloration there anymore. And you will be seeing a precipitate being formed. Now, the precipitate that is formed is this 2,4,6 tribromoaniline. 2,4,6 tribromoaniline. Now, if you remember, if you go back to your textbook, you would remember there was a similar reaction observed in another organic compound. And that compound was phenol. Now, phenol is also, just like nitrogen here, is capable of activating the benzene ring. So therefore, it will also react with bromine the same way. it will form 2,4,6-tribromophenol, which is also going to be a white color precipitate. So a similar observation is going to be made here as well when it comes to aniline. With bromine, it will be forming a white color precipitate, and the color of bromine will be disappearing as the reaction proceeds. So you can see through these images, aniline, if you take a small amount of aniline into a test tube and a small amount of bromine into a test tube afterwards, you will see as they react, the color of bromine, brown coloration of bromine, will disappear, and you will be seeing a white color precipitate being formed. So that is another way that you can test the presence of aniline. The bromine water is brown in color. As it reacts with aniline, the brown color will disappear and a white color precipitate will be formed. A white color precipitate will be formed. So as I mentioned earlier, and we have looked at the diagram as well. This again is an electrophilic substitution reaction. We can see none of the double bonds were broken. You can see we don't necessarily have double bonds in benzene. We have, this is the Kekulé structure for benzene. However, you can see what has happened here is a hydrogen that was connected to the carbons at 2, 4, and 6 positions in the benzene ring have been replaced by bromine. So this is a substitution reaction, and it is not any substitution reaction, it is a electrophilic substitution reaction, and the electrophile happens to be Br plus ion. Electrophile is Br plus ion. Now let's move on to the next reaction. Preparing benzene diazonium salt starting from aniline. So we are going to be starting this reaction from aniline and then reacting it with phenol in alkaline medium. Right, so we are going to start it with aniline and we are going to form benzene diazonium salt, and the benzene diazonium salt that is formed is going to be reacted with phenol in alkaline medium. And what we will be forming is an azo dye. And the color of the azo dye will depend on whether we are reacting it with phenol or whether we are reacting with beta-naphthol. If you are going to be reacting with beta-naphthol, we will be getting a red color dye. But when it comes to phenol, we will be getting an orange color dye. Now, how we conduct this experiment is given here. Let's go through the steps and take a look at the important details that are found in these steps. They say dissolve about 5 or 0.5 grams of aniline in 3 cubic centimeters of concentrated hydrochloric acid and 1 cubic centimeter of water. Now you might be asking, why are we using aniline and concentrated hydrochloric acid? Yes, as I mentioned earlier, aniline does not dissolve in water. So how do we improve the solubility of aniline in water? By adding HCl. So HCl will react with aniline to form phenylammonium chloride, which is soluble in water. Then place the mixture in an ice bath. Why do we place it in a mixture? What is the reason for placing this in the mixture? In this mixture in ice bath? The reason for placing this mixture in the ice bath is the reaction where we form the benzene diazonium salt needs to happen at 0 to 5 degrees Celsius. Imagine one of the reactants that you are trying to add to this mixture is at room temperature, and while you are keeping the other one at 0 to 5 degrees Celsius ice bath. So room temperature mixture, when they come into contact with 0 degrees Celsius, let's say another reactant solution, what happens? The temperature of the mixture will get elevated because we added a solution that was at a higher temperature or at room temperature. So then we will not be observing the formation of benzene diazonium salt. So whenever we are carrying this reaction out, before mixing the two reagents together, we have to make sure that the two reagents we are mixing are at the right temperature, which is between 0 to 5 degrees Celsius, right? So that needs to be done. So that is why as we form the relevant reagents, we are placing each of these mixtures in an ice bath. Then let's move on to the second point. Dissolve about 0.2 grams of sodium nitrite in about 2 cubic centimeters of water and cool in ice bath. So we are going to take sodium nitrite and dissolve it in water. We don't have trouble dissolving it in water. It will dissolve really well. And we also place it in an ice bath. In the same ice bath, we can place both. When it comes to the third point, we can see they ask us to dissolve about 0.2 grams of phenol in 5 cubic centimeters of 10% sodium hydroxide. Now we are asked to use sodium hydroxide to dissolve phenol. Now phenol also is not very water soluble. So then what do? We will dissolve it in sodium hydroxide. Now this entire reaction needs to be carried out in an aqueous medium. So therefore this phenol and all other organic substances that are not very soluble in water should be made soluble in water. So we saw when it comes to aniline, we reacted with HCl. So therefore now aniline is now turned into phenylammonium chloride, which is soluble in water. Or when you say aniline, it is phenylamine. So phenylamine goes from being phenylamine to phenylammonium chloride. When it comes to phenol, when phenol is capable of releasing an H plus ion. So when phenol is reacted with sodium hydroxide, it will release an H plus ion and will form the phenoxide anion. And with sodium hydroxide, so basically phenol will form sodium phenoxide, or the phenoxide anion will be soluble in water. So therefore, we are using sodium hydroxide and phenol together. We will be dissolving phenol in 10% sodium hydroxide, and the resultant solution will again be placed in an ice bath to cool down. And in the fourth step, they're asking you to keep the aniline and HCl mixture. They ask us to keep the aniline and HCl mixture in the ice bath itself, and then to it they ask us to add cooled sodium nitrite solution slowly to the mixture, stirring the mixture well. So you have to make sure you stir the mixture really well. And apart from that, we are going to be keeping the aniline and HCl mixture in the ice bath, and we are adding sodium nitrite and HCl solution to our aniline and HCl mixture. And as you do this, you will be forming a benzene diazonium salt. We will be forming benzene diazonium chloride. And this solution that is formed will appear pale yellow in color. So they say the pale yellow color solution obtained at the end of this step is benzene diazonium salt. Now in your practical book, you might notice the same information being there. So now let's move on to the final step. In the final step, they ask us to add the previously prepared alkaline phenol solution to benzene diazonium salt while keeping it in the ice bath. So normally we will be keeping our benzene diazonium salt in the ice bath, and we will be adding phenol that is dissolved in sodium hydroxide to our benzene diazonium chloride solution. So as you can see, phenol is in alkaline medium and phenol is being added to the benzene diazonium salt here. So between the benzene diazonium salt and phenol, there's going to be an electrophilic substitution reaction taking place, making our SO dye. So what is the color of our SO dye? It will be forming a bright orange color. So what we form here is your azo dye, and the bright orange color that we observe is due to formation of p-hydroxy azobenzene. So while doing this reaction also, you have to make sure that the reaction mixture is stirred really well. Now let's take a look at reaction that is taking place here. We started off with aniline, and we converted aniline into a benzene diazonium ion by reacting it with sodium nitrite and HCl. And we made sure to maintain a low temperature between 0 to 5 degrees Celsius. How did we do this? By keeping all of the mixtures in the ice bath, not the water bath. Ice bath made sure that this particular temperature was maintained. And then afterwards, when you are adding a benzene diazonium chloride with phenol, you are going to be forming this compound. You are going to be forming p-hydroxy or para-hydroxy azobenzene. So this coupling reaction takes place when these two reagents are added together. Now students, keep in mind, we are conducting this experiment and the final step actually in alkaline medium. So as we know that the hydroxide ion that we have in the alkaline medium may react with the phenol, and you might not get the product with OH here, right? You might obtain this product where instead of having an H, bear with me a second, instead of having a hydrogen, you might obtain this product that I'm drawing here, which is O minus. So you have a tendency of obtaining, instead of obtaining para-hydroxy azobenzene as mentioned earlier, this phenol or OH group can become an O minus group because this medium is alkaline. So the OH group can react with the alkaline medium and can form O minus ions. But this is not a problem for us. We can easily convert this back into OH by adding a little bit of an acid. So in all of these steps that we discussed, whenever we said p-hydroxy azobenzene is formed, we wrote OH. But in reality, what happens is the compound that is formed can have an O minus, or the OH group that we see over here can react with the alkaline medium to form this. However, this can be resolved by adding a little bit of acid to reform the OH group. Now let's take a look at some images of what is going to happen. We will be doing this in the lab. However, before going to the lab, you need to have an idea about how it is going to be done in the lab. So we have benzene diazonium salt that is formed. It is going to be in the ice bath. So how did we form the benzene diazonium salt? We took aniline, reacted with HCl, now it is in one test tube, and then we had sodium nitrite, and we mixed them together and we formed this pale yellow color solution, which is our benzene diazonium salt solution. So we keep it in the ice bath. Now this is our ice bath. You can see a beaker filled with ice. And then we have our phenol in the alkaline medium. We made this by dissolving phenol in 10% sodium hydroxide. And now we keep them until that temperature drops below 5 degrees Celsius. So their temperature should be between 0 to 5 degrees Celsius. And afterwards, we will be adding our phenol in alkaline medium. Phenol in alkaline medium will be added to our benzene diazonium salt, while keeping the benzene diazonium salt in our ice bath. And then what happens is, and while doing this, you have to make sure that you stir the solution. And while doing this, when you are pouring your phenol in alkaline medium, you will be observing the formation of an orange azo dye, right? You can see orange color azo dye is being formed here, and it is going to be the compound para-hydroxy azobenzene. In this slide, students, we are going to be looking at why we carried out certain steps when it comes to conducting this practical. The first one that we are looking at is going to be the reasons behind the dye formation reaction is carried out in an alkaline medium. And now, students, we have discussed this reason in prior slides as well. Benzene diazonium salt is an aqueous solution. It is going to be produced as an aqueous solution. Phenol or beta-naphthol, whatever the secondary solution we use, do not dissolve well in water. They do not dissolve well in water. Since the reaction between the reagents need to take place in an aqueous medium, right? So these reactions, they need to take place in an aqueous medium. Sodium hydroxide is added to facilitate the dissolving of phenol and beta-naphthol in water. Now we know phenol has an OH group that is capable of releasing its H plus or releasing the hydrogen. So in an alkaline medium, this will be facilitated, and phenol will be forming phenoxide anion. It will be forming phenoxide anion. In the presence of sodium hydroxide, it will be forming sodium phenoxide. So phenoxide anion or sodium phenoxide that is formed is soluble in water. This same thing happens to beta-naphthol as well. The OH group in beta-naphthol will be turned into O minus ion, which will increase its solubility in water. So the reason behind using an alkaline medium when it comes to this reaction is mainly to dissolve these water non-soluble substances in water. So when it comes to phenol and beta-naphthol, they'll be dissolving better in an aqueous sodium hydroxide medium. So that is why we use a sodium hydroxide medium. And then we move on to another question that is there, which is, can similar dyes be produced using aliphatic amines? So what did we learn about aliphatic amines? Aliphatic amines, can they form an aliphatic diazonium salt or aliphatic diazonium ion? The answer to that would be no, right? We can't form a aliphatic diazonium salt. Aliphatic diazonium salts are unstable. They will directly be turned into an alcohol. So when you're trying to convert an aliphatic amine into aliphatic diazonium salt, what you will be forming is an alcohol. You can't form the aliphatic diazonium salt. So to form an azo dye, you would need a diazonium salt, and therefore you can't use an aliphatic amine to form a similar dye. A similar dye cannot be formed with the use of an aliphatic amine. Unlike aromatic amines, aliphatic amines do not produce a stable diazonium salt. Due to this, similar dyes cannot be formed with the use of aliphatic amines. Similar dyes cannot be formed. Similar dyes cannot be formed with the use of aliphatic amines. Now, with that information, students, we conclude the theory part revolving around this experiment number 23. Now, we are going to step into the lab and actually conduct this experiment. Let's move on to the lab now. GCE Advanced Level Chemistry Practical Series, experiment number 29. tests for aniline. The aim of this practical is to identify aromatic primary amines by the reactions of diazonium salts. And we are going to be forming azodies through diazonium salts. Now, let's go ahead and identify the reagents and the equipment we will be using for this practical. In this practical, we will be using aniline, also known as benzenamine or phenylamine. We'll be using concentrated HCl acid, bromine water, sodium nitrite, phenol, sodium hydroxide. We'll be using wash bottle containing distilled water, test tubes, a thermometer to measure the temperature, and some ice. We'll be using ice bath in this experiment, so you'll be using ice in a beaker to cool down our solutions. Now, let's move on to the first part of our practical. In the first part of our practical, we are going to see how aniline reacts with water, bromine water, and how it reacts with HCl. Now, let's take our aniline. We have aniline over here, and we are going to add a small amount of aniline into a test tube. We can see the color of aniline is going to be ranging from yellow to orange. So this is a yellowish orange color that we see. Now, let's add a small amount of water to see if it is soluble in water. If it is soluble in water, it will not form two layers. If we can see a layer separation, that means aniline is not soluble in water. As you can see, when a small amount of water is added, it is not forming a homogeneous solution. It is forming two layers, indicating that aniline is not soluble in water. Even if you mix it, we can see small droplets of aniline forms, and then they come together to form a single layer of aniline. Now, let's take another small portion of aniline into a different test tube. And to this, we'll add a small amount of water so that we can clearly see what happens when we add HCl. So we can see when small amount of water is there, we can very clearly see the layer separation. Now, let's add a small amount of HCl. So we have our concentrated HCl over here. Let's take our concentrated HCl solution, and we'll add a small amount of concentrated HCl to see what happens when we react HCl with aniline. As you can see, when we add HCl, little by little, the aniline starts to react. So, acid that we have over here, which is HCl, reacts with the base aniline and forms a salt. The salt that is formed is referred to as anilinium chloride. And as you can see, it dissolves well in concentrated HCl and forms a solution. When aniline is reacted with hydrochloric acid, we form a salt which is anilinium chloride. and it is soluble in water. As you can see, there is no layer separation. That means when we react HCl with aniline, the salt that is formed is soluble in water. Let's see how aniline reacts with bromine water. We have our bromine water here. Let's take a small amount of bromine water into a test tube. The bromine water we have here, as you can see, is a yellow-brown color. Bromine is red-brown in color. So when it comes to bromine water, depending on the concentration, you will have either a very strong yellow-brown color or a bit of a pale yellow-brown color. However, this bromine water, if it shows a reaction with aniline, the color of the bromine water should disappear. Aniline, just like phenol, activates the benzene ring. So therefore, it readily shows a reaction with bromine water. Just like when it comes to phenol, aniline also forms a white color precipitate after reacting with our bromine water. So therefore, you will see the color of the bromine water disappearing as well as formation of a white color precipitate. Now, let's take aniline and add a few drops of aniline into this bromine water solution. As you can see, upon addition of just a single drop of aniline, we can very clearly see the formation of a white color precipitate. When bromine reacts with aniline, it forms 2,4,6 tribromoaniline, which is going to be a white color precipitate. And as you can observe here, the color of the bromine water disappears slowly. So if you mix it a little bit, you can see we do not observe the color of bromine water anymore. It is completely transparent. However, we have the white color precipitate forming, which is 2,4,6 tribromoaniline. So this is the observation when you react aniline with bromine water. Now, let's move on to the next part of our practical. In this part of our practical, we are going to use aniline and produce benzene diazonium salt, and through this salt, we are going to form an azo dye. First, we are going to take aniline. We are going to take about 0.5 cubic centimeters of aniline. Now, we have taken about 0.5 cubic centimeters of aniline into a test tube. We can add 5 cubic centimeters of concentrated hydrochloric acid to this aniline. We have our concentrated hydrochloric acid here. Now, as you can see, we are adding concentrated HCl into an aniline sample that we have here. When we add concentrated HCl, it dissolves readily in concentrated HCl and forms a salt, anilinium chloride. We have to add about 3 cubic centimeters of concentrated HCl. As you can see, we have completely dissolved the aniline that we had in the test tube. Now we have produced a salt, which is anilinium chloride, in this test tube. So now we'll allow this sample to cool down. It has to cool down below 5 degrees Celsius. So we are using an ice bath to cool down the sample below 5 degrees Celsius. After dissolving aniline in concentrated hydrochloric acid, we are now going to take sodium nitrite and dissolve it in water. We have our sodium nitrite over here. We'll take a small sample of sodium nitrite. We'll transfer it to a test tube. And now we'll dissolve it in water. If 2 milliliters of water isn't enough to dissolve it, we can add a little bit more water. And after completely dissolving sodium nitrite, we can place it in the ice bath to cool this solution also below 5 degrees Celsius. Now we have two test tubes here, one containing aniline and hydrochloric acid, the other one we have our sodium nitrite solution. Now, after preparing our sodium nitrite solution, we are going to prepare our phenol solution. We have our phenol sample here. We are going to take a small amount of phenol and we are going to add 10% sodium hydroxide to it. Let's take a dropper and take about 0.5 milliliters of phenol. And to that, we are going to add 10% sodium hydroxide. We will be adding around 5 milliliters of 10% sodium hydroxide. Now, as you can see, when we have added around 5 milliliters of sodium hydroxide, we can see all of the phenol dissolved in the sodium hydroxide and formed a solution. Phenol is acidic in nature, and when you react sodium hydroxide with phenol, we produce sodium phenoxide salt, which is soluble in water. So what we have here is sodium phenoxide. Now we will allow that sample also to reach temperatures below 5 degrees of Celsius by placing it in a water bath. Now we will allow it to cool down for a while. While the samples in our test tubes cool down, let's talk about the reaction that is taking place over here. So we have aniline dissolved in hydrochloric acid And to that sample, we are going to add sodium nitrite. Sodium nitrite in the presence of aniline and HCl will produce benzene diazonium chloride. This is also referred to as an aromatic benzene diazonium salt. Benzene diazonium chloride or aromatic diazonium chlorides are more stable than aliphatic diazonium chlorides. However, if the temperature is not kept between 0 and 5 degrees, at higher temperatures, this benzene diazonium chloride will turn into phenol, nitrogen, and hydrochloric acid. So you can figure out if you have done the reaction at a higher temperature and if we have produced benzene diazonium chloride or if we have produced phenol by a few observations. If we have produced phenol instead of benzene diazonium chloride, you will see the formation of nitrogen gas bubbles, or your observation would be the formation of gas bubbles. And when we have produced benzene diazonium chloride, the solution that is produced is going to look a pale yellow color. So after producing benzene diazonium chloride, while keeping this solution between 0 to 5 degrees Celsius, we are going to react it with alkaline phenol solution. So in the alkaline medium, we are going to see benzene diazonium chloride react with phenol to produce an azo dye, which is going to be orange in color or red in color. So color may range between orange and red. So now let's observe if the solutions have reached the required temperature, we can start mixing sodium nitrite with aniline solution that is reacted with HCl. Now we can use our thermometer and we can observe the temperature of our aniline and HCl solution. We can see the temperature is going down. And at present, the temperature is between 0 to 5 degrees Celsius. It is around 3.5 degrees Celsius. Now that we know the temperature is between 0 and 5 degrees Celsius, let's take our sodium nitrite and aniline mixed with hydrochloric acid and let's mix them together. We have to keep stirring them while you mix it. And we have to make sure that we keep the temperature between 0 and 5 degrees Celsius as well. So we have to make sure that these test tubes remain in the ice bath for the most part of this experiment. So while keeping it in the ice bath, we can add our sodium nitrite. And as you can see, we are forming a yellow color solution. This yellow color solution is our benzene diazonium chloride solution. Students, now we have made benzene diazonium chloride. So we have an aromatic benzene diazonium salt, which is benzene diazonium chloride that is formed here. And you can see it is yellow in color. And we have to make sure that we keep it in the ice bath as much as possible because this is stable under low temperatures. At high temperatures, this will turn into phenol, nitrogen, and HCl. So we'll take a portion of our benzene diazonium chloride into another test tube. And to this, let's add our alkaline phenol solution. We have our phenol mixed with 10% sodium hydroxide solution over here. Now we are going to add phenol mixed with 10% sodium hydroxide into our benzene diazonium chloride salt. Now you can see as soon as we added it, we saw the formation of a red color dye. So this red color precipitate that is formed is our azo dye. This is our azo dye. We keep it here. We'll allow it to cool down for a while and we'll observe it again after a while. Students, now we have allowed the mixture to react properly at lower temperatures, and we can see the color of the dye that we have formed. And you can see what we have formed is a precipitate. You can see by observing the walls of this test tube, the precipitate that is formed is a red-orange color. So this is more towards red than orange. So what we have formed here is p-hydroxy azobenzene, which is azo dye. So we formed this azo dye through benzene diazonium ion. Now this is a test that we can use to identify aniline. In summary, let's take a look at what reaction we looked at today. Initially, the first part of this practical, we took aniline and we dissolved it in water. And upon addition of water, we realized aniline forms two layers with water, indicating that it is not soluble in water. Then we moved on to adding concentrated hydrochloric acid to aniline. Aniline is a base and therefore it reacts with the concentrated hydrochloric acid, forming anilinium chloride, which is going to be a water-soluble salt. So upon addition of HCl, we saw that aniline dissolved in HCl. Now, afterwards, we added bromine water to aniline. Upon addition of bromine water, the color of bromine water, in our case, the color was pale yellow-brown color, and when we added aniline to it, we saw the color of bromine water disappeared while forming a white color precipitate, which was 2,4,6 tribromoaniline. Afterwards, we moved on to forming our azo dye. In the first step of forming the azo dye, we had to form our benzene diazonium ion. Benzene diazonium salts are usually unstable. At room temperature, if you carry out this reaction, benzene diazonium salt will not be formed. However, when you mix aniline in the presence of HCl and sodium nitrite, if we carry out this reaction at lower temperatures, we saw that we are forming benzene diazonium chloride, which is our diazonium ion. And while maintaining lower temperatures to this benzene diazonium chloride, we added alkaline phenol or phenol in an alkaline medium. When we added phenol in alkaline medium into our benzene diazonium ion solution, it formed an orange-red color precipitate, which was our azo dye. So this is how we identified the presence of aniline. Now, let's move on to other theory parts revolving around this practical and some questions that is revolving around this aniline practical. Now, students, we have looked at the theory parts that is revolving around experiment number 29, and then we went into the labs and conducted the experiment. Now we are here again to take a look at some questions that are revolving around the theory parts of experiment number 29, tests for aniline. Now let's take a look at the first question. First question, they are saying that there is a compound that is containing a CH3 group as well as an NH2 group connected to a benzene. They say the basicity of the above compound is lower than the basicity of methylamine. So we are given with this question, basicity of the above compound is lower than the basicity of methylamine. And the second statement says the CH3 group connected to benzene is capable of attracting electrons towards itself. Now let's take a look at these answers. The very first statement, is it true the basicity of this compound is lower than the basicity of when it comes to methylamine? Now students, let's talk about how an amine is capable of acting as a base. The basicity of an amine depends on how easily the lone pair found on the nitrogen can be donated to NH+. So if you have a proton here, how easily this lone pair can be donated determines whether this amine that we have here is high in its basicity or whether it has a lower basicity. When it comes to primary amines such as the one that they have given here, CH3 NH2, this CH3NH2 on nitrogen, you can see on the nitrogen you'll be able to observe that there's a lone pair. And the CH3 group is known to be an electron releasing group. It releases electrons towards the nitrogen. The bond electrons are released more towards nitrogen, making it easier for the nitrogen to donate the lone pair of electrons to an incoming H+. So as the electrons are released more towards nitrogen, the electron density around nitrogen will increase sufficiently to the point that these lone pair of electrons can be donated to an H+ with ease. They will be producing CH3 NH3+. Methylammonium ion will be produced. From methylamine, methylammonium ion will be produced. Now, when it comes to aniline or phenylamine, which is a primary aromatic amine, this is a primary aliphatic amine. So, when it comes to this phenylamine or aniline, we are going to observe resonance structures. You can see the lone pair on the nitrogen atom that we have here is going to be incorporated into the delocalized electron cloud. And if you are taking a look at resonance structures, you are going to observe that the lone pair of electrons that we have here, is going to be donated here to form a double bond, and the electrons that we found over here will be given to the carbon that is present in this position. And since the lone pair of electrons are present here, we are going to have a carbon with a negative charge, and then this pair of electrons will be donated here. And while that is happening, you can see, since carbon can't have more than 4 bonds, you will see that this double bond will break to give its electrons here. We can see now a double bond is formed in this position. You will be observing there are lone pair of electrons in this carbon, and then these lone pair of electrons will be donated here, causing this double bond to break, and then we will get to this resonance structure. Now students, this is the reason, or forming these resonance structures are the reason why the lone pair of electrons that we found on nitrogen is not freely available to be donated to and incoming H plus. So you don't have these lone pairs freely available to be donated to NH plus. So the ability that aniline has to accept a proton is less compared to the ability methylamine has when it comes to donating the lone pair of electrons to NH plus. So when you are comparing the basicities of aniline to methylamine that we have here, since methylamine will donate this lone pair of electrons with much ease compared to aniline to NH plus, this is more basic. And phenylamine or aniline is less basic compared to methylamine, because phenylamine's lone pair of electrons are now incorporated in the delocalized electron cloud of benzene. We explain that with the use of resonance structures that we see here. According to what we have just learned, we now know that the very first statement that we have here is correct. Why? They say the basicity of the above compound, which is this compound, is lower than that of methylamine, which is true. We have a lower basicity that we have here. So therefore, when you move on to the second statement, they say the CH3 group connected to benzene is capable of attracting electrons towards itself. No. Now, when it comes to CH3 groups are actually capable of releasing electrons from it. And therefore, this statement is false. That statement is false. And students, since we predominantly looked at only aniline, I want to tell you here, if you had the CH3 group attached here, it would not make a difference. We will still have these resonance structures with our CH3 group connected here. It wouldn't make a difference, right? There will be CH3 groups in either of these places, actually each of those places, and it will not make a difference to the resonance structures. And at the same time, the main key piece of information that you should take away from this is that the nitrogen's lone pair is not going to be freely available to be donated to NH plus, and that fact will not be changed due to the presence of CH3 group here. So the first statement is correct. Our first statement is correct. However, the second statement is false and does not explain anything as well. So the answer is, first statement is true, second statement is false. Answer is going to be 3. Answer is going to be 3. Now students, let's take a look at the next question. Phenols react with the following. Now we have been given a few compounds and we are going to be looking into whether these compounds can be reacted with, or whether phenol is reacting with these compounds. Now we have a methyl group connected to a benzene as well as a diazonium salt. So this is a benzene diazonium salt. Obviously, we know now benzene diazonium salts will react with phenols to produce azo dyes. So therefore, this compound that we have here will definitely react with phenol. This compound will definitely react with phenol. No problem there. What about dilute nitric acid? Now, dilute nitric acid also reacts with phenols, right? So we have that equation here. When it comes to dilute nitric acid reacting, even at room temperature, it will react to form orthonitrophenol and paranitrophenol. As you know, the OH group that we have here, is activating the ring mainly at the ortho and the para positions. So therefore, you will see that we are going to be forming orthonitrophenol and paranitrophenol when it comes to this reaction. So yes, the answer to this question to this question is yes, dilute nitric acid will be reacting with phenol. What about dilute HBr? No, HBr cannot react with phenol. There's no reaction observed when it comes to HBr, and you wouldn't see any reaction with a compound like this, dinitrobenzene. You will not be seeing a reaction with that kind of compound as well. So this is also not going to be showing any reaction. These two will not be showing us any reaction. So the answer for this question is going to be A and B only. And there is an answer like that. A and B are correct. For this question, the answer would be 1. Only A and B are correct. So this kind of question should be easy for you, since we have learned about benzene diammonium chloride, and you would have learned about dilute nitric acid reaction with phenol as well. So you should be able to answer this type of question. Let's move on to the third question. In the third question, they're asking bromine water reacts with the following through a substitution reaction. So bromine water would react with the following reagents through a substitution reaction. So phenol, when it comes to bromine water and phenol, what is the chemical reaction we see? You can remember bromine water and phenol can easily react together to form, now we have phenol here, and if you add bromine water, what would you get? You would observe 2,4,6 tribromophenol. You will observe the formation of 2,4,6 tribromophenol, and this is a white color precipitate. You will be observing the formation of a white color precipitate. Right, so yes, phenol will react with bromine, and the precipitate formed is going to be formed through a electrophilic substitution reaction. The hydrogens present in the 2, 4 and 6 positions will be replaced by bromine. So this is a electrophilic substitution reaction. And then they are asking again, we are being asked whether it is going to react with, whether bromine is reacting with benzene. Have we learned about any reaction where benzene and bromine directly react with one another? No. So therefore, benzene and bromine will not directly react with one another without a halogen carrier. Benzene and bromine will not be reacting directly with one another. What about aniline? We'll move on to aniline. Does aniline react with bromine? The answer is yes. Just like aniline, just like benzene and bromine reacted with one another, aniline also will react with bromine. So if you have aniline here, and if you react it with bromine water, or bromine for that matter, you'll be forming a similar compound to what we saw earlier. But in this case, the similarity is where the bromine groups are going to be connected. 2nd, 4th and 6th positions. You will see bromine being connected there. You will be forming 2,4,6 tribromo aniline. This is also a white color precipitate. This is also a white color precipitate. So what we form here is 2,4,6 tribromo aniline. Earlier what we formed was 2,4,6 tribromo phenol. So you can see similar structures. However, the names are different. We will be observing the same observation, which is a white color precipitate will be formed and the color of bromine water will disappear. Bromine water is brown in color. You will not be seeing the color after this reaction has proceeded and produced these products. Then another compound is here, which is this styrene. Will bromine water react with styrene? Now, what is the formula of styrene? So let's take a look at the formula of styrene. Styrene looks like this. Now we have the benzene ring, you have styrene that has this structure. And now students, when you hear the word styrene, you might have already thought about polystyrene, rigid form. So polystyrene is formed through this molecule, styrene. And styrene molecule has a double bond. And what do you know about a double bond reacting with bromine? Yes, if you had already thought of it, double bonds will react with, when it comes to alkenes, alkenes will react with bromine water. Alkenes will react with bromine water to produce this compound. Bromine water will be decolorized and bromine will be added. Bromine will be added across the double bond. Halogenoalkanes will be formed. Now students, this is not a substitution reaction. Although bromine water will react with styrene, what you have here is not a substitution reaction. You can see the double bond opened up and accepted bromine. So therefore, this is going to be a addition, or it is going to be an addition reaction that is taking place when it comes to bromine. It is not a substitution reaction. And the question asks us, bromine water reacts with the following through a substitution reaction. So when it comes to styrene, since it is reacting with styrene through an addition reaction, styrene cannot be taken as an answer. So the answer would be phenol and aniline, A and D. Only A and D are answers. So therefore the answer would be 4. Let's move on to the next question. In the next question, we have aniline here. They have given the formula. And we have cyclohexene here. Aniline and cyclohexene here. They have given the skeletal formula here. Two different organic compounds. What reagents out of the reagents given below can be used to separately identify these compounds? What reagents can be used to identify these two separately? Can we use neutral ferric chloride? No, neutral ferric chloride does not react with either of these. But what about cooled potassium permanganate solution? When it comes to cooled potassium permanganate or potassium permanganate in an alkaline solution, we can see the formation of a diol if there is a carbon-carbon double bond present. So we do have a carbon-carbon double bond here. Do we have a carbon-carbon double bond here when it comes to phenylamine? No. When it comes to phenylamine, there is no carbon-carbon double bond. So therefore, you can separately identify these two with the use of KMnO4. As you know, when it comes to a double bond, I will briefly give you an idea. Now we'll take a different example for this. If you take ethene and reacted with KMnO4, what you will be obtaining is a diol. You will be obtaining a diol where across the double bond, two OH groups will be connected. Ethene diol will be formed. So when it comes to the answer, you can see cooled potassium permanganate solution is an answer. Cooled potassium permanganate solution. When it comes to cyclohexene, potassium permanganate will react with it to form a diol here. Across the double bond, two OH groups will be connected. And if you are conducting this experiment in alkaline medium, you will see that potassium permanganate that has a purple color will turn to a brown color precipitate. Permanganate ions will be turned into MnO2, which is a water insoluble brown color precipitate. So the color of potassium permanganate, purple color, will disappear, and the observation would be a brown color precipitate will be formed. So that can be used to identify cyclohexene separately from aniline, because aniline will not provide that observation. So B is an answer. Can we use aqueous bromine? Yes, we can use aqueous bromine, as this will give us two different observations. Aqueous bromine will give us two different observations. What are the two different observations that you will be seeing here? When it comes to aqueous bromine, if you take aniline, if you react it with Br2, we saw what happens. Aniline will produce a white color precipitate, which is 2,4,6 tribromoaniline. So let's draw it here. We will be producing 2,4,6 tribromoaniline. And this is going to be a white color precipitate. What will happen to the color of bromine? Br2 will be decolorized. So from brown color, the color of bromine, which was brown in color, will be colorless now. So it goes from brown color to being colorless while producing a white color precipitate. But can we say the same about cyclohexene? Cyclohexene will be somewhat different to that. So cyclohexene, when you are reacting it with bromine, again bromine water is going to be brown in color or red-brown in color. But as you react it with cyclohexene, what will be formed is that will undergo an addition reaction, and we have bromine connected to this cyclohexene across the double bond. And will we be observing a precipitate? No precipitate. There won't be a precipitate, but the solution will be colorless. So the lack of a precipitate here will give us an idea that we are actually reacting bromine with cyclohexene. Because if we had reacted bromine with phenylamine or aniline, we will be observing a white color precipitate apart from observing the solution turning colorless. So we can use aqueous bromine to identify these two compounds separately. What about sodium hydroxide? Is there a reaction that you observe with sodium hydroxide? Do you see a color change when you are reacting these two things with sodium hydroxide? No. There won't be any observations when it comes to reacting sodium hydroxide with either of these compounds. So therefore, the answer is going to be B and C, which is going to be our second answer. So the answer is B and C. So the second answer will be the correct answer for this question. Let's move on to the question number 5. Now in the question number 5, we have two statements and we have to figure out whether the first statement is true and then whether the second statement is explaining it and whether it's true or false. Right, so let's take a look at the first statement. First statement, aniline will take part in an addition reaction with bromine water to produce white precipitate. So what do we know about aniline and bromine water? Now we looked at this type of question in the previous slide as well. So we see aniline will take part in an addition reaction with bromine water to produce a white precipitate. So there are two parts in this first statement that is true, which is aniline will react with bromine, no problem there. Aniline and bromine will react with one another. Aniline will react with bromine for sure. However, when they are reacting, they will also form a white precipitate. These two things are true. But we do have one false statement or one false part in the first statement, which is they say when these two are reacting, the reaction that is taking place is an addition reaction. So is it true? No. When it comes to aniline and bromine reaction, we saw that the reaction that is taking place is a substitution reaction. Hydrogen in the 2, 4 and 6 positions of aniline get replaced by bromine. It does not follow through an addition reaction. Instead, it actually takes part in a substitution reaction. So since this part of the statement is false, this entire statement is false. It is not a true statement. There are two parts that actually make it look like it is true, but then again, there's one part in the statement which is false, making the entire statement false. And then we have bromide will be added to aniline through the double bond of aniline. As we know, when it comes to benzene's Kekulé structure, although we draw the benzene with the Kekulé structure, benzene actually do not have double bonds. All of the pi electrons of the benzene ring are delocalized, so therefore they are not going to have double bonds. So when you're adding bromine to aniline or when you're adding bromine to phenol, we will not be adding bromine to aniline or phenol with the help of an addition reaction where the double bond is broken. It is going to be a substitution reaction. The hydrogens are going to be substituted. So the answer, or when it comes to this statement is also wrong. Why is it wrong? They say bromine will be added to aniline through the double bond. No, there is no involvement of the double bond of aniline, or there are no double bonds in benzene. Which we are observing is the delocalized electron cloud, and the double bonds that we draw when it comes to drawing benzene is the Kekulé structure that was given initially for the structure of benzene. And now we know that is not how benzene actually is. So therefore, the second statement is also wrong. So the response would be this: false. First statement is false and second statement is false. Answer would be 5. Answer would be 5. Let's move on to the next statement or next question. When it comes to the next question, we have again another question with a similar format. First statement says aniline cannot be directly reacted. Aniline cannot be directly reacted with bromine to produce 4-bromoaniline. So we have to again explore the reaction of aniline. So when you are adding aniline to bromine or bromine to aniline, actually, what we observe is this reaction. We have aniline here. That is reacting with bromine, And you will observe the formation of, as I mentioned earlier, we have seen this reaction multiple times when it comes to these questions. We'll be forming 2,4,6 tribromo aniline. We have seen the formation of 2,4,6 tribromo aniline. If this is the carbon number 1, this is 2, 3, 4, 5, and 6. So now you observe, students, here, when it comes to this structure, this is going to have bromine connected to 2nd, 4th, and the 6th carbon. We do not form a compound where bromine is only connected to the 4th carbon or para carbon. So therefore, we can actually say that this statement where they say aniline cannot be directly reacted with bromine to produce 4-bromo-aniline, which is true. We can't produce only 4-bromo-aniline. What we actually form is 2,4,6-bromo-aniline. This is what actually get formed. You can't form only 4-bromo-aniline. So therefore, the first statement is true. Second statement, benzene ring is strongly activated by the NH2 group. Yes, and that is the reason why we can't form this. When it comes to NH2 group being directly connected to our benzene ring, this activates the benzene ring mainly in the ortho and the para positions. Now, let's take a look at this structure again. So we can see over here we have in the ortho and the para positions, these are our ortho positions and we have our para position here. You can see when NH2 is added to the benzene rings are going to be having a higher electron density mainly in ortho and para positions, and due to that, due to activating the benzene ring in such a way, forming only 4-bromo-phenylamine or 4-bromo-aniline is not going to be feasible. It is not going to be possible. So the answer over here, when it comes to this particular statement, what they have mentioned is actually true. And apart from it being true, it also explains the first statement. Since benzene ring is strongly activated by the NH2 group in aniline, you can't form just 4-bromo-aniline. You will end up forming a white color precipitate which is 2,4,6 tribromo-aniline. So in this case, the statement is true. The first statement is true. Second statement is also true, and it correctly explains the first statement also. Therefore, the response should be 1. 1 should be our response. Now let's move on to our next question. In the next question, we are going to be talking about the reaction where we produce a diazonium salt. So let's take a look at it. When B, which is an organic, B is an organic compound which is reacted with sodium nitrite and HCl at this temperature, 0 to 5 degrees Celsius, nitrogen gas is released. When the resultant solution is reacted with beta-naphthol in alkaline medium, a red color was formed. Red color precipitate was formed, and they ask you to identify B. Now students, we know a red color. By now you should know a red color precipitate is formed when beta-naphthol in alkaline medium is reacted with this type of product is going to be due to a reaction between beta-naphthol and a benzene diazonium salt. There should have been a benzene diazonium salt reacting with beta-naphthol, because the resultant product is a red color precipitate, or red coloration was observed. So red color precipitate will be formed only when, especially when we are already having beta-naphthol in the reaction mixture. It should have reacted with a benzene diazonium salt. So we know benzene diazonium salt was here. So, however, you can see when we are trying to start with organic compound B and form a benzene diazonium salt by addition of sodium nitrite and HCl at this temperature, nitrogen gas was released. So why would that be? Imagine if B was only this, if our B compound was simply aniline, will there be a reason to produce nitrogen gas? Let's see. When you're reacting aniline with NaNO2, sodium nitrite, and HCl at these temperatures 0 to 5 degrees Celsius, what you will be forming is benzene diazonium chloride. This is what you will be forming. Do we see the formation of nitrogen gas here? No, we will not be forming nitrogen gas here. However, if you remember the theory parts we have studied, we learned when an aliphatic amine, it reacts with the same conditions, NaNO2 plus HCl, along with the same temperatures, actually 0 to 5 degrees Celsius. You will not be forming a benzene diazonium, or you will not be forming an aliphatic diazonium salt. You will be forming an alcohol instead, and along with it, you'll be forming N2 gas and HCl. N2 gas will be formed here. So students, keep in mind that when it comes to this situation, you have to remember nitrogen gas is formed when an NH2 group is connected to an aliphatic carbon. But if the NH2 is directly connected to an aromatic group, at that point we are dealing with aromatic amines. Aromatic amine can form a diazonium salt. Aliphatic amines cannot form a diazonium salt. You will be forming an alcohol along with nitrogen gas. So this indicates that you had a nitrogen or NH2 group connected to an aliphatic carbon as well, and you have to have in the same compound B, you have to have a nitrogen group directly connected to an aromatic carbon as well. So let's take a look at a situation like this. So in the first answer, your amine group is connected directly to our benzene ring, so it fulfills one requirement, but it doesn't have another amine group connected to an aliphatic carbon. So therefore, this first answer cannot be our answer. First answer can be removed from the set of answers that we have here. It will not be considered. The second answer, you can see the nitrogen here is directly linked to the benzene ring, so it can form the benzene diazonium salt. However, we don't see the nitrogen gas releasing group, which is a carbon group connected, or aliphatic carbon group connected to an amine group. We don't see that part here. So therefore, the second answer is also not going to be considered. Let's take a look at the third answer. In the third answer, you see that the NH2 group is directly connected to the benzene ring, making it an aromatic amine. However, when it comes to this NH2 group that we have there, it is connected to a CH2 group, and the CH2 group is connected to the benzene. So NH2 group over here is not directly connected to our benzene ring, making this an aliphatic amine. So this section is forming an aromatic amine, and NH2 connected to CH2 is making an aliphatic amine. So what do we know about aliphatic amines? If you take this compound to the side, and if you see what type of reaction would take place, if you take the compound that we have in answer 3, you have an NH2 group directly connected here, and we have a CH2 group connected to the benzene, and that CH2 group is connected to an amine group. So when you are reacting this compound with NaNO2 along with HCl at 0 to 5 degrees Celsius, you are going to turn this amine group that is directly connected to benzene, which is a aromatic amine group, into a benzene diazonium group. But what about this section? That section, since this is an aliphatic amine, aliphatic amines, as we know, will turn into an alcohol. And in turning into an alcohol, that section will also produce nitrogen gas. So the answer to the question that they asked is also this. They are saying compound B, when reacted with sodium nitrite and HCl, was able to produce benzene diazonium chloride as well as nitrogen gas. For benzene diazonium chloride to be produced, an amine group should be directly connected to the benzene ring, forming an aromatic amine. And to produce nitrogen gas, there should be a section which happens to be an aliphatic amine. So this compound has both. Therefore, the answer to the question that they have asked should be 3. Answer should be 3. So this should be our answer, but let's explore the other answers as well to see if there's more than one answer to this question, which is highly unlikely, but still we'll go through it. You can see again, we see here an aliphatic amine, which is only going to be able to produce nitrogen gas. And on the right hand side of the compound, you have a OH group, which is not going to be turning into a diazonium ion. So therefore, we can't use that for this question as the answer. When it comes to the fifth answer also, you can see an NH2 connected to a CH2, not directly connected to the benzene ring. So this is a aliphatic amine. And what about this one? This is also an aliphatic amine group. And the other group that is present here is OH group, which is not going to be able to turn into a diazonium ion. So therefore, answer 5 cannot also be considered. 4 and 5 cannot be considered as the answer. Only correct answer would be 3. Now let's move on to our 8th question. 8th question, they have given us 2 amines. And what is the series of reactions that can be used to identify the 2 amines separately? So we are trying to identify these 2 amines separately by using either one of these series of reactions that we have here. Now students, let's take a look at these two amines. We have the first amine where we can see the nitrogen is connected to an aliphatic carbon, and in the second amine also it's a aliphatic carbon that the nitrogen is connected to. So we don't have any aromatic amines formed here. So we have two CH3 groups connected to the central carbon, and then we have nitrogen connected to that. So let's draw this. We have carbon here connected to a benzene and two CH3 groups. Then we have NH2. And then we have another compound where we have benzene connected to three CH2 groups. CH2, CH2, CH2. And eventually it is connected to an amine group. Now both are primary amines. Can you react primary amines with anything to separately identify them when it comes to a situation like this? No. Now we have learned about how to identify when it comes to aromatic amines and aliphatic amines, how to separately identify them. When it comes to both primary amines, if you're trying to identify them separately, it could be difficult. So we would be reacting them. Now they say this is reacted with sodium, we use sodium nitrite, and HCl. So since both of them are aliphatic amines, you will be forming alcohols. The first one will be forming this alcohol. The first compound when reacted with nitrous acid. So when sodium nitrite and HCl is reacted, you will be forming nitrous acid. You will be forming this alcohol. And the second compound will be forming the following alcohol. Now students, if you observe closely, you would notice that these are two different alcohols. These are two different alcohols. They might have the same number of carbon atoms, but their structure is different, to the point that it forms, the first compound has formed a tertiary alcohol. You have formed a tertiary alcohol. And the second compound has formed a primary alcohol. Tertiary and primary alcohols are formed here. Now, at this point, you should clearly see how we can identify these two compounds separately. Right, students? So first, we noticed that we can't keep these amine groups and continue with the reaction, right? So one of the experiments that we can do to convert them into alcohols is using sodium nitrite and HCl. So at that point, you'll be forming alcohols. So what is most important is somehow getting these primary aliphatic amines to react with nitrous acid. So at that point, since we can't keep the NH2 groups and try to separately identify the two compounds, we have now converted these amine groups to OH groups by reacting them with nitrous acid. So at that point, we have two different compounds. We have a tertiary alcohol and a primary alcohol formed. Now, how do we distinguish between a primary and a tertiary alcohol? You would remember reagent called Lucas reagent. So Lucas reagent, when Lucas reagent is added, what happens? So first of all, we'll quickly go back to the question. So first step that we followed was identifying that when it comes to separately identifying these two compounds, we need to have these NH2 groups converted into OH groups. So that's the first step. For us to do that, we have to have nitrous acid. So we have to focus out of these given answers, which answers actually can be used to convert NH2 into an OH group. Can we use the first reagent in the first answer? Yes, we can. So we can keep the first answer. What about the second one? Potassium nitrite and HCl. When you mix them together, it will form, definitely it will form our expected reagent, which is, or our expected product, which is alcohol. So we can keep the second answer as well. Third answer, you have nitric acid and sulfuric acid. Can we use the third answer? No, we can actually cancel it. We can't use the third answer. What about the fourth answer? Yes, we can use the fourth answer, because again, fourth answer is sodium nitrite and HCl, which is going to be turning it into nitrous acid. So nitrous acid, when reacted with NH2, will form an alcohol. What about the fifth answer? Again, they are using nitric acid. So nitric acid is not going to be used. So you can't go with the third and the fifth answer. So we will remove them, or we will not consider those answers. But apart from those, then we are given few other answers. So if you are taking these sets of answers as possible answers, then we have to take a look at the second step to identify tertiary alcohols and primary alcohols separately. They are saying nitric acid can be used. Can we use nitric acid to identify them separately? No. So therefore, the first answer is also wrong. But about the second answer? Second answer, they say HCl and zinc chloride, or anhydrous zinc chloride. Can we use that to identify primary and tertiary alcohols? The answer is yes. This is what is referred to as our Lucas reagent. So Lucas reagent is zinc chloride and HCl. When it is added together, you will be reacting them, and when it comes to tertiary alcohols, they will be forming an halogenoalkane like this: CH3, CH3 over here, and the benzene group is going to be present over here along with a Cl. Now this reaction will happen quite fast. When it comes to Lucas reagent, you will see that the tertiary alcohols react with it the fastest. Primary alcohols will not react with it that fast. So you will not observe a specific observation when it comes to primary alcohols. So when it comes to tertiary alcohols reacting with Lucas reagent, this produced product, which is the halogenoalkane, is not very soluble in water. So therefore, you can see the solution turning cloudy. You will observe the solution turning cloudy. We can write solution turns cloudy. Solution turns cloudy, and this is a test that we can use to identify the tertiary alcohol. What happens to primary alcohol? You will not be observing a reaction. When it compares to the tertiary alcohols, you will not be observing a reaction fast reaction happening in primary alcohols. You will not be observing turbidity or cloudiness in the solution that we have the primary alcohol in. So in the solution where we have the primary alcohol, when you are reacting with Lucas reagent, you will not be observing very special observation like this one. You will be observing when it comes to tertiary alcohol, due to forming this halogenoalkane, which is water insoluble, the solution will turn cloudy, and that observation can be used to identify these two compounds separately. So the series of reaction that can be used would be the second series of reactions. What about the fourth one? We didn't take a look at it yet. Nitric acid and sulfuric acid. And now normally we use this when it comes to trying to add NO2 groups to benzene. So here you will actually not see a reaction taking place with our alcohols that we have here. So therefore, the fourth answer is also not going to be the correct answer. Correct answer is the second answer. So it is very important not only to remember theory parts revolving around aniline or theory parts revolving around amines. It is also important to remember other theory parts, like how to identify primary and tertiary alcohols, because this type of questions sometimes appear where they are not only questioning the theory parts revolving around aniline or theory parts revolving around amines. They will also sometimes include parts that test your knowledge on other organic compounds like phenols, like alcohols, carboxylic acids, so on. Let's move on to the next question. Bromine water reacts with which of the following? And this is a simple question. When it comes to bromine water reacting with an aromatic compound, especially a compound that contains benzene, benzene ring needs to be activated. So when it comes to all of the compounds that are present here, most of them are not going to be activating the benzene ring. So the first one is a ketone group that is present here. This is not activating the benzene ring, so that is not an answer. The second one is nitrobenzene, not activating the ring. You can see here a fluorine group is connected to the benzene. Again, electron withdrawing groups will not activate the benzene ring. However, OCH3 group is having a lone pair of electrons here, which will get incorporated into benzene ring and therefore increase the density of electrons or electron density in the benzene ring and therefore activate the benzene ring. So the answer to this question is 4. This activates the benzene ring and therefore it will react with bromine water easily, producing a substitution product. So answer is 4, and obviously since all the other answers are wrong, fifth answer is also not considered. So answer for this question is 4. Let's move on to our next question. What reagents can be used to initiate a reaction to separately identify these two compounds? So they are asking you what reagent can be used to initiate a reaction. You need to initiate a reaction to separately identify these two compounds. The first one is a aliphatic amine, and the second one is an aromatic amine. So how can we identify an aliphatic and an aromatic amine? How do we identify these two? If you remember, we discussed when it comes to an aliphatic amine, such as this one, we can identify an aliphatic amine by whether or not it actually can form a diazonium salt. We know aliphatic amines can't form a diazonium salt. Apart from that, we would see when it comes to, we have here our actual aromatic amine. So if this aromatic amine is reacted with nitrous acid, you will be forming a diazonium salt in the right temperature, which is 0 to 5 degrees Celsius. So if you take both of these compounds, and then react them with sodium nitrite and dilute HCl and carry out a reaction between 0 to 5 degrees Celsius temperature, you will be observing that this compound is turning into an alcohol while releasing nitrogen gas. So you can see the formation of a gas here. So that is one observation which can be used to identify when it comes to the first compound. The first compound can be separately identified when you are carrying this reaction out. However, when it comes to the second reaction, you will see this reaction will be forming a benzene diazonium ion. This will not be forming nitrogen gas, so therefore you will not be seeing a formation of a gas here. But since this formation of a gas might not be very clear, we can take it a step further. To identify them very clearly, we can react both of the products that are formed. Now we don't know which one is the aliphatic amine, or let's say which one is the aromatic amine. It's in two samples that are not labeled, two beakers that are not labeled. So after reacting both of these solutions with sodium nitrite and HCl and in this temperature, the resultant products can actually be reacted with alkaline phenol solution. So we can take phenol in alkaline solution, or we can write in NaOH. So then at this point, you would say the benzene diazonium salt will react with phenol to produce parahydroxyazobenzene. So although we don't need to know about the names, we can actually observe the color here. So the observation is when phenol in alkaline medium reacts with benzene diazonium salt, you will be observing a colorful precipitate being formed, or colorful suspension being formed. So you will see here an orange color suspension. The resultant reaction mixture will change its color to orange. Orange color azo dye will be formed. What about this reaction? If it reacts with phenol in sodium hydroxide, will we be forming any colorful compounds? No. No observation. So this can be used to identify these two compounds separately. So in order for us to identify it, first of all, we need to have a nitrite ion reacting with HCl. So do we have a nitrite ion here? Let's go through the answers. So if you take a look at these answers, the first one is an acyl chloride, ethanoyl chloride. Ethanoyl chloride, can it react with these amines and form a color, or give us a color change? Although it reacts with the amines, it cannot be giving us a color change. So that because of that, ethanoyl chloride can't be used. Again, we have another acyl chloride. Again, all of these acyl chlorides cannot be used to identify these two separately. Why? Because we are not going to be getting a color change. A color change is required because that is going to be our observation to identify, or maybe a formation of a precipitate, or maybe formation of a gas that is evolved. So none of that happens when it comes to the reactions with acyl chlorides. Just a halogenoalkane like this will also not be suitable because it is also not going to react well with any of these compounds to give us a color change. But what about potassium nitrate? Can potassium nitrate be used? So the answer to this question is actually potassium nitrate. I said all of these answers cannot be correct for this question. Even the fifth answer is wrong. The correct answer is the fourth answer. Why might that be? Because it says potassium nitrate. So you will be now conflicted. I said earlier that we need to have a nitrite ion, right? We need to have a nitrite, not a nitrate. So how can we initiate a reaction to identify these compounds with potassium nitrate? So the answer is in the question. Initiate a reaction to separately identify these two compounds. So you can use potassium nitrate. We can use potassium nitrate and if you heat it, you'll be forming potassium nitrite and oxygen. So this is the reason why potassium nitrate is the answer to this question. And at the same time, you would again notice another nitrate here, ammonium nitrate. So again, you'll be conflicted. So if it is a nitrite ion that is going to be forming this, why didn't we take ammonium nitrite or ammonium nitrate? The reason why ammonium nitrate is not the answer is because when it comes to ammonium, NH4, NO3, when you heat it, you will be forming different products. Nitrous oxide, N2O, and you will be forming H2O, water. You will not be forming the required nitrite ion. You will not be forming the required nitrite ion. So therefore, the answer to this question is going to be the fourth answer, potassium nitrate. The answer to this question is potassium nitrate. And we explained the reason behind that. Now students, let's move on to the next question. Now we have the 11th question. Let's take a look at it. When an organic compound called A was boiled with concentrated hydrochloric acid and allowed to cool, a white crystalline solid B was formed. Now students, after reading the first sentence, you should remember when it comes to adding a strong acid to a weak acid's anion, what happens? The weak acid will be displaced. And why I bring that point up here in this question is because they say when you added a strong acid, a concentrated strong acid, a white crystalline solid was formed. So students, when you're studying organic chemistry, one of the white crystalline solids that get formed in such a manner in the presence of concentrated acid is going to be a carboxylic acid, or actually aromatic carboxylic acid. So what you have formed here, by looking at this, you should be able to remember in the presence of a strong acid like this, an aromatic carboxylic anion can actually turn into an aromatic carboxylic acid. And then we have that acid formed here. And then the next step they say, when B was filtered and washed with water and reacted with sodium bicarbonate, air bubbles formed. So this is a confirmation for us to understand that the B, now B precipitate, white color B precipitate was removed, and then it was washed with water to remove any impurities, and then it was reacted with aqueous sodium bicarbonate. So bicarbonate is normally used to identify the presence of a carboxylic acid. So air bubbles confirm it, right? As you react bicarbonate with a carboxylic acid, you will see the formation of carbon dioxide and water. So this sodium bicarbonate will turn into bicarbonate ion, will turn into carbon dioxide and water. When sodium nitrite was added to the filtrate, now the filtrate is what you obtained after the B precipitate was removed. So we formed a B precipitate and you removed it, and what we were left with was the filtrate. So if you add sodium nitrite to this filtrate, you will be, first of all, they say they add sodium nitrite, and then aqueous ammonia was then used to neutralize the solution. And afterwards, when bromine was added to this neutral solution, a white color precipitate was formed. We know two precipitates that are normally formed or normally forming white color precipitates. We know two precipitates that are normally formed when bromine is added, that is 2,4,6 tribromo phenol and 2,4,6 tribromo aniline. So we have to remember those two pieces of information as well, because it will be helpful in trying to identify what A could be. So let's dive into this question. Now you can take a look at the answers also. All the answers contain phenol groups, and you can see amide links here also present. So we could be having a reaction, or we could be having a compound that contains both a carboxylic acid group and a NH2 group, right? So let's take a look at it. So now students, when it comes to HCl being added, if you are talking about a compound like this, if you have a carboxylic acid anion, when H plus is added, this will turn to an aromatic carboxylic acid. Which will not be very soluble in water. So therefore you will have this precipitate as a white color precipitate. Now this white precipitate that is formed is benzoic acid, which is an aromatic carboxylic acid. This could be one of the possibilities, but this possibility would not explain to you why when the filtrate is reacted with sodium nitrite and then after that neutralized with ammonia and then reacted with bromine would precipitate out as a white precipitate. So this doesn't explain that part of this question. This structure explains why you would be forming a white precipitate in the very first step when you added HCl. The second portion of the question is not explained through this observation. So this tells us it is not just a carboxylic acid anion that could be present here, right? It could be something that, or some sort of bond that gets broken in the presence of concentrated hydrochloric acid and heated is there. So if you take a look at an amide bond that looks like this, amide bond that might be present like this, could be, just could be, one of the reasons why we are forming, in the second portion, why we are forming a white color precipitate. Why do you think that this is not going to be just NH2, but it is connected to a benzene ring? We know towards the end of the second portion of this question, we are going to be forming a 2,4,6 tribromo white color precipitate. It could be 2,4,6 tribromo aniline, or it could be 2,4,6 tribromo phenol. To produce either one of these, you should have an NH connected to a benzene. That is why we assume that it could be something like this. So let's pay attention to what happened to a compound like this when we are reacting it with concentrated HCl, and if you heat it in the presence of concentrated HCl, you can see a hydrolysis reaction taking place where you will be forming a carboxylic acid group by breaking this bond that we have here. This bond will be broken, and apart from that, you will be forming NH2 connected to a benzene, or in other words, aniline or phenylamine. Now students, although we write it like this, although we write phenylamine like this, keep in mind this phenylamine is going to be formed in a strong acidic medium. So phenylamine, if we write it over here, phenylamine that is formed, is going to be present in this form, phenylammonium chloride. As phenylamine reacts with HCl, you will be forming phenylammonium chloride. So in the beaker where you mixed the carboxylic acid, in the beaker where you mixed our concentrated HCl along with the organic compound A, you'll be seeing a precipitate that is formed, which is going to be your benzoic acid. And in the filtrate, you will be having this ion. We will be having that ion if the compound we are dealing with is actually this. So after figuring this out, now this is our white color precipitate. This is our white color precipitate. And after that, so this is what you have in the filtrate, but we know as it reacts with HCl that is present in the medium, right? We are dealing with a concentrated HCl medium. So concentrated HCl in the medium will convert this into NH3Cl or phenylammonium chloride. And then they say in the next part of the question, let's take a look at what they say. After B was formed, then we saw the B is reacting with sodium bicarbonate. It's a very simple reaction. We know very well the benzoic acid is capable of reacting with, benzoic acid is capable of reacting with sodium bicarbonate, and it will produce the anion of the carboxylic acid and water along with carbon dioxide. Sodium benzoate is what is going to be formed along with water and carbon dioxide. So students, this is the reason why you see gas being formed, or we can see here they say air bubbles were formed, and the air bubbles that are getting formed here is carbon dioxide. Then sodium nitrite was added to the filtrate. So the filtrate contained phenylammonium ions, and sodium nitrite is added to the filtrate, and aqueous ammonia was then used to neutralize the solution. Now, if you can remember, students, I told you in this solution, the solution that we had over here, when benzoic acid was formed, we saw in the supernatant or the filtrate, we have this ion, and this ion is still acidic. HCl is still there. And after the filtrate has been removed, let's say we remove the filtrate, so we'll take this filtrate off. So let's say we remove the precipitate, which is our benzoic acid. In the filtrate, you will still have these two compounds. We'll have phenylammonium chloride and we will have HCl. And to this, we are adding sodium nitrite. What do you think could happen? So in the presence of sodium nitrite, you will see that this phenylammonium chloride will react to form a diazonium salt. But we know very well the diazonium salts at room temperature are not stable. So normally, how do we form a diazonium salt? We will be taking our aniline and we will be reacting it with sodium nitrite and HCl. But if you are doing this reaction at room temperature, then what do we form? We will be forming phenol. We will be forming phenol. But the same reaction also can be done by first converting the aniline molecule that we have here into phenylammonium chloride. And then reacting it with, now in this medium you have enough and more HCl, right? You add HCl here, and then if you add NaNO2, sodium nitrite, you can convert it into phenol at room temperature. So both of these things are, both of these reactions can be done at room temperature. You can directly convert it to phenol by adding both of these reagents together, or else you can add one reagent at a time and convert it to phenol. So either way, at the end of this reaction, what you have formed is phenol. And then you will be neutralizing it with ammonia, because we know still there could be a lot of H plus ions in the medium. So we have to add a base to remove the H plus ions or neutralize it. And after neutralizing it in the medium, you are going to only have phenol. There won't be any H plus ions in the medium. You will only have your phenol. So to this phenol, if you add bromine, you will get what? You will get 2,4,6. You will get 2,4,6 tribromophenol, which is a white color precipitate. A white color precipitate will be formed. So students, this is the answer to the question. So the question is, what is the compound A? So the compound A should be what we have drawn here. This should be our compound A. We should have a benzene group connected to a C double bonded oxygen group, and then we should have an amide bond between carbon and nitrogen, and to that nitrogen you should have another benzene group connected. So the answer for that question is going to be given here. You can see answer number 3, right? We can see the same structure that we drew over there is present over here. right? So the answer for the question that is asked in this 11th question is 3. Now let's move on to the next question. It is a very simple question. Let's take a look at the simple question that we have here. Consider the compounds given below. We have aniline or phenylamine, we have ammonia, and we have ethylamine. Arrange these compounds in descending order of basicity. So you can see, we know very well when it comes to amines, their basicity depends on how easily they can donate their lone pair of electrons that is found on nitrogen. And when it comes to these given compounds, now when it comes to donating nitrogen becomes easy if there are electron releasing groups attached to nitrogen. So ammonia has a moderate amount of basicity, but if you take ethylamine, now ethylamine contains an alkyl group that is capable of releasing electrons towards nitrogen, increasing the electron density around nitrogen, making it easier for nitrogen to donate the lone pair of electrons. So the basicity of ethylamine is greater than the basicity of ammonia. However, we have another compound which is aniline. Now aniline, we learned earlier, the lone pair of aniline or lone pair that is found on the nitrogen of aniline is actually incorporated into the benzene ring. We learned about the resonance structures, and then we learned that when it comes to aniline, the nitrogen's lone pair is not freely available to be donated to a proton. So therefore, the basicity of aniline is far below the basicity of these two. So aniline's basicity is the lowest out of the given options. So we have methylamine, which is having the highest basicity, and in second place you will have ammonia, and the lowest basicity is observed when it comes to aniline. So what answer explains that to us here? So aniline, and then ammonia, and finally, we have methylamine, ammonia, and then aniline is the answer 3. CBA is the answer 3. So for this question, the answer is 3. Now students, we have completed discussing the questions revolving around practical 29. And in the beginning of this practical, we looked at the theory parts revolving around this practical, and then afterwards we moved on into the lab and we conducted the experiments and observed the observations we should be making, and now we came here to discuss some questions. And after discussing these questions, I hope you have developed a really good understanding about how to answer questions revolving around amines, aniline, and even phenol. So that will be all for this practical. I will see you again in the next practical.